sort of mapping as you were interviewed by the New York Times.
Yeah.
You didn't make it to the article.
Good.
Yes.
Yeah.
We will tell us more about type theory. So.
Cool. Yeah. Are we good?
Yeah.
Yeah. No pressure. Yeah. So this is going to be 0 to type theory in 1 hour. So I don't know how experienced everyone is with type theory. I'm assuming that all of you know quite a bit, but just in case, I'm going to start at the very beginning. I've been told that it's better to ramp slowly up than to lose everyone in the first 5 minutes. So that's going to be the philosophy. Okay. Let's see. I just made these slides pretty recently, so I don't remember what's on the next slide. So we're going to find out together. All right. Here we go. So we got 3 statements. They have something in common. I'm going to ask you all to figure it out. First, computer science finally let us formally verify proofs. Second, type theory is an advanced branch of mathematics with esoteric prerequisites. And third, proofs are esoteric artifacts that hold universal laws. Anyone have an idea? Yes? Right?
I was going to say false.
Not only false, but...
What's in common?
I just think it's a criminal lack of hanging indents. Because those double quote marks need to be off to the side, so it's C is over you.
Okay, yeah, I will run my slides by you from now on.
Something you heard software engineers say.
Well, I think you got it. They're all false, but they're all backwards. So, in some sense, computer science exists because of formal methods. And I'll go into exactly how it is in the future. Second, you really don't need to know much math to understand type theory, and in fact, I think that the most difficult part for most people is just how simple it is, and how little grasp you can get from using other techniques to think about, the very base of everything. And then connected to that, proofs are social artifacts, and formal methods are ways to develop more and more trust in those artifacts. But at base, it's, do people trust what I'm saying, and do they have reason to believe that it's true? Anyway, all right. So, recently at a conference, I got asked this question by someone who knew nothing about lean, and I had to stop for a while because it's actually a really, really tricky question. So in some sense, formal methods and proof existence are the reason that computers exist in the way that we think about them today. And recently there have been, of course, a bunch of developments with Rock and Lean and whatnot. So I'm going to go through the historical reasons that these things exist, starting at kind of some arbitrary points. And that should hopefully motivate some of the later discussion of, like, why do we care about type theory? What are these paradoxes, and what do they have to do with, everyday mathematics? All right. So first, I'm just going to choose to start in 1879 with a guy called Frege. So he wrote this book with this beautiful syntax that nobody uses, which is kind of a shame. It's beautiful. But this was the first appearance of quantified variables. So you have things like for all x and for all p holds of x.
Have you replaced Hey Google with Hey Frege?
maybe. Yeah, so this represents the starting point of analytic philosophy. Anyway, yeah, so from here, there's this kind of historical pattern of just fuck around and find out, where like we propose these systems with nice notation, and we usually think that they're sound, consistent, that they can eventually prove everything that is true, and then someone finds a paradox, and then you make a change, and that's kind of a large part of the history of type theory from now on.
What was Frege trying to do?
Nothing less than develop a set of axioms and a notation for formally specifying logic. I guess, any more questions? Is this too basic? Is this too advanced? No? Cool. All right. So Russell's paradox. This is in response to Frege. You might notice that there were about 22 years between when this was proposed and when this paradox was at least publicized. So the basic idea behind Russell's paradox, I'm not going to explain the whole thing, it has to do with quantifying over all things. So you can say things like the set of all sets that do not contain themselves. So that's what this is. You have x, which is supposed to be implicitly quantified. So you have x does not contain x for all of those things. This is set comprehension. Take all x's such that x does not contain x. So if you think about what happens here, I'm sure a lot of you are familiar with the paradox, but if x is not in x, then it is in x, and vice versa. So the received wisdom from this, at least within type theory, is whenever you can quantify over all things, you can usually do bad things. So this is going to motivate the discussion of universes later on. An interesting corollary of this is that Zermelo, so the Z in ZFC, also knew about this paradox at about the same time. And so this was really the start of the type theory, set theory, I don't want to say war, but the difference in opinions. And you've already heard from Elliot, so let me tell the other side. All right. So after that, there were these two huge mathematicians, but Hilbert is, he was like the emperor of mathematics back then. Had this philosophical disagreement. They're both pretty stubborn, but Brouwer ended up being kind of ostracized because he took the side of intuitionism, which is a very strong version of constructivism, against Hilbert's formalism. So what do those mean? The formalism is Hilbert would set out to exhaustively specify all the axioms for example, geometry. And the idea is you have all these axioms, you can combine them in whatever you want, and they will eventually encompass all of the true things about geometry and none of the false things about geometry. Brouwer basically said, some of those axioms allow you to tell me that constructions must exist without actually handing them to me, and that's not good enough. So the idea behind intuitionism and largely constructivism is if you claim that something exists, you have to actually hand me the thing. So this is, it's a philosophical distinction, and the larger distinction is, so I'm repeating this from a professor, but anyway, Brouwer kind of stands on the side of proofs are human communication artifacts, as in you really have to help people understand exactly what you claim to exist, whereas Hilbert is more on the side of, we should figure out all the true things, and anyway, this will become clearer later on, but there's this distinction, and sort of ironically, type theory has largely coincided with Brouwer's view, which I'm going to stop myself. We'll get into this later on. Right.
Why, starting from the premise you said that proofs are human artifact that we help communicate to each other, why does that mean it has to be constructive, I guess, missing that part of connection? Because formal proofs can also be a communication tool, I guess.
Yeah, it doesn't necessarily, and this ties into a lot of the discussion around the axiom of choice. So we have, for example, theorems like in game theory, there's always a Nash equilibrium, but we don't necessarily know how to find it. And so that's a concrete place where these two would disagree, where in an intuitionistic logic, you couldn't prove that there is always a Nash equilibrium because you can't show it to me. Whereas with the formalist view, you can say there always must be one, and so there always is one. Whereas constructivism rejects a bunch of equivalent axioms kind of that flavor. Does that make sense?
Yeah.
Okay. Cool. Any other questions? Right. This seems a bit abstract. I didn't do a great job explaining it, but in the interest of time, I'm going to move on. All right. So Hilbert set out a bunch of problems for the mathematical community, which is a huge research program that practically everyone who's anyone worked on. One of these was the Entscheidungs problem, which is basically, in modern parlance, is mathematics decidable? Like, is there a machine where you can take some statement S, run it through this black box, and then get either yes, S is true, or S is not true, and ideally a logical proof that S actually is true or is not true. So the interesting thing about this is this is phrased as a effective procedure. So there has to be essentially something in the box. This is before computers, so someone can just follow a set of steps, and you have to write out what the steps are. So a lot of the process of solving this problem is not cannot really proceed until you define something like what is an algorithm. So that motivated the lambda calculus. It's not well known, but the lambda calculus is a fragment of what Alonzo Church was trying to develop, which was a logical system. The logical system that he developed was proven inconsistent by Klein and Rosser in 1935, but this survived because it's a very, very good model of what we think of as all possible computation. And it's remarkably simple. It's just either variables, lambda abstractions, or applications. This is equivalent to Turing machines, and the Church Turing thesis says that any kind of computing machinery can be reduced to a Turing machine, which is equivalent to this. So this is pretty remarkable. Way back in the day, way before computers were practical objects. Anyway, so Church and Turing were working on the Entscheidungs problem. So this is often forgotten in CS curriculums. So the basic thrust behind this argument is that to show that the Entscheidungs problem is not true in general, you just have to pick out one specific problem where you can't make the thing in the box. And that one specific problem is the halting problem. So, the thing that we all learn about in CS curriculums, for those of us who took CS, was really just kind of a toy construction in the middle of what they saw as a more interesting proof, which was in the realm of pure math and formal methods. So that's kind of, it's a provocative statement, but that's why I said that formal methods are the reason that computer science exists, because this is kind of the modern foundation of computer science. Very briefly, I think it's a long paper, but you can get kind of 80-20 by just looking at this paradox. So if you say the Entscheidungs problem is solvable, there exists some black box, then you can use it to solve the halting problem. If you can use it to solve the halting problem, then you can write a Turing machine that solves the halting problem. You can write this as a Turing machine, and if you run it on itself, and you ask, does this paradox halt? Then if it says that itself halts, then you loop forever, you don't halt. And if not, then you return immediately halt. And so this thing always produces a paradox, and so therefore Entscheidungs problem is unsolvable. So, the brief upshot of this, to be provocative, is that CS started its side quest for formal verification. Right. Cool. So I'm just gonna survey the audience and say, is this a good pace? Yeah? Okay, cool. All right. Inference rules. This is the thing that everyone tells me not to do, and everyone tells everyone not to do, but they're not scary. And so I'm just gonna spend like 5 minutes showing you what inference rules are, how to read them, because you're going to see them if you look in the type theory, and they're really not scary, but nobody ever explains how to read them, they just assume. So I'd like to, do what I wish that someone had done for me 3 years ago and explain this thing. So here's an inference rule. You've got a line, a bunch of statements on top, and there can be multiple things, but 99% of the time there's one thing on the bottom. And so the way that you read this is if P and Q and ... and Z is true, then you can infer that C is true. And so you might be wondering why there's a line here. I'll get to that in a bit. But the nice thing is that it's kind of symmetric, where you can read top to bottom as because PQ ... C is true, I can apply C. And if you have something like this, then you can say, I know that C is true because of PQ ... C. So you can do things. Yep.
Leading question from the dumb guy. This would also be what we call conjunctive normal form, because we're just seeing a series of premises and it's always handed.
Yep.
And the way that you've written this, would this mean that P, Q, and Z are all known as well as the conclusion at the end, or are you forgetting them all as you go to the conclusion? In this
I don't think I follow the question.
Well, do you still have P, Q to Z as well as the conclusion in the conclusion, or is that conclusion as like a logical state? Does that exist only as the conclusion? You've forgotten all the premises.
I think I know what you're asking. So theoretically, if you have P, Q, and Z up here, that means that you've derived P, Q, and Z.
Mm-hmm.
So you kind of throw them away at the bottom.
Yeah.
But since you've derived them, you can basically take the derivation and copy it somewhere else. And so there are There are systems where it matters that you're throwing them away, and there are systems where it doesn't matter. So technically you are throwing away PQ and Z, but in most systems you can rederive them somewhere else by following the exact same thing you did. Cool, any other questions? Great, all right. So, why do we have the line? Because we can do something like this. So, this is a derivation tree. So if you look at, count up the number of lines, you see that there are really 5 inference rules used here. And so the names on the right tell you what rule was used to go from the top to the bottom, or from the bottom to the top. So here, for example, this is a proof that false or true, and true or false. So the cool thing about this is you can see this as either starting from nothing and building up to this theorem, or asking if this theorem is true and then showing why. So that's mainly the reason that inference rules are ubiquitously used instead of things like, literally writing and implies. You can do things like this. Is this relatively clear to everyone? Are there questions? Yeah.
Is there a relation between this and like abstract data type constructors?
Yes, I'll get to that.
Because it seems like statement, bunch of construction rules, perfectly fine.
Yeah, you're onto something.
Confirming, so far there's no time, previous question notwithstanding. Right, we're not.
Yeah, this is kind of, taking a God's eye view, and, if you gave, Terence Tao 100 years, could he come up with a derivation tree? Yeah. I think I saw another, yeah. No? Cool, all right. So, moving away from that, so this is something that you might see on a specific line. So this also probably looks scary. I promise you it's not scary. This is a turnstile, and so it means if A has type A, and B has type B, and everything to the left of the turnstile. And so I'm just using these to show operator precedence. Then you can apply, you can conclude that Z has type C. So this is how you would write typing rules. This is kind of meaningless at the moment because you don't know what A, B, and Z are, and there's no real structure here. But when we see typing rules, and I promise this will be over soon, this turnstile just means everything on the left implies the thing on the right. So it's kind of like the line, but laid out horizontally. Good?
Is it just the same as the line, but a different notation, or is it different?
It's acting like the line, logically, but we will want to have typing derivations where we say, something has type T because, and then there's a derivation above. So we write these horizontally so that we can have them above the little line. But it's still the same, like if A has type A and B has type C, and then we can apply this one thing on the right.
Everything on the left is like context, and sometimes you kind of like conjoin all the context into like a context symbol, and you just have like gamma turnstile, and it means like anything that was known previously, and then you move to the next thing.
Yeah, but it sounds like it's not exactly like the line, which is similar. It's like you could.
They're different notation for the same thing.
They are.
Yeah, the useful, and the thing that they're notation for is just all of the things on the left imply the thing on the right, or all of the things on top imply the thing on the bottom. We just write them horizontally or vertically, and with different symbols to denote that they're kind of part of different universes of things.
Is one of them like a large step and one of them a small step? There are single steps in this derivation, and you can combine them. Does that apply to both symbols?
So,
If you go to the previous slide, right?
yeah.
I can say from nothing, basically can I collapse this whole thing and say from nothing I have the final expression at the bottom, because there are intermediate steps that I can skip.
You could, but it's useful to note that, like, for example, here there are 2 things above the line. Here there's 1. Here there's nothing.
Right, so can I compress it into a single, like nothing, line, 0, and so. Is that a valid notation?
You could. It's not a precise notation. If it's obvious,
And what
people
about
probably know what
turnstile
you mean.
Is the turnstile, does that also not allow that?
Yeah, so the turnstile, you can imagine that all of these would have their own derivations. So I think maybe we should work through an example.
Yeah.
Okay. Do I have one?
Well, if
Yeah.
very brief comment. If you go back to the previous version of where's that? It is a reminder that these are, I'm curious if the following statement would be true or help the slide move forward, that in the end though, these are all still social tools to persuade each other as human mathematicians. If you simply wrote blank, horizontal line, and then the last thing on the slide, it wouldn't be very persuasive to anybody, right? I mean, that's a simple trivial thing we're proving, like the point is to see that, saw that. So it's your choice about it. It's a matter of style and as I said, simple and hard, these are all taste things we're gonna find out, but yeah, just because you could mechanically rotate one or the other doesn't mean you should.
Yeah, sure. So you could write dot dot dot, like
Right.
it's obvious that.
Right.
Yeah,
But the
something like
notation
this.
exists to decide what is obvious,
Yeah.
and what is obvious depends on whom you're talking to.
Yeah, and this will be something that we can mechanize as a proof system. So that's that's why the precise notation matters.
The one question, just
Yeah.
between each of the lines, there's notations. How does that apply in when you have the turnstile?
Yeah. Between each of the lines, do you mean stuff like this?
Yeah.
Yeah. I guess you could name reasons that things have types. That's not something that's usually done. It's more like, so the turnstile kind of acts like the and here, where it's within the language of the things that are below and above the line. And so once you have something that you know is true, you can kind of ignore everything that's above. So maybe I led you down the wrong path by saying that it's kind of like the line. Yeah, I guess for now let's just think about it as, like, let's say you're in the middle of writing the body of a function, and you define some variables, and those variables have certain types. Then you can say it's valid that the return value for this function has some type, given that I use x, y, and z that I found above. So that's what the turnstile means. Given that all of these are in context, and I know their types, then I can say that z does have type z, and z might use A, might use B, might not. I think this will be clear if we go through an example now. So, okay, cool. I would also be happy to drop this if people are falling asleep. Okay, cool. So, here is a rule which says that if you have something in context, then you can use it. That's simple. Here, this is falling below the line, but it's exactly the same thing. So if we have something like f has type from A to B, meaning f is a function that takes an A and returns B, that's already in the context, so we can use f has type A to B. And what this rule means, which is arrow elimination, I'll get into that one. You can take an A, you can take an f, and if A has the type, the argument to f, then f of A has the type, the return type. So is this helping or is this hurting? Yeah.
So I'm trying to figure out if some of the notation is just like a mistake on the slide, or if that
It
is
is.
doing something. So
Yeah. It's a mistake on the slide. This should all be down here below the line.
It's line right.
You can ignore this for now.
That's better.
So the way, sorry. Yeah.
I think you can make progress. I'm getting playing usefulity here. If I think of A as a point in two-dimensional space on an XY grid, a Cartesian coordinate system, and f is some function like distance from origin, like length, then like the length function, or the distance function, then if I have A as a point in 2D space, then the left-hand side is saying I could use that, it's a point, 2D point, and the right-hand side is saying the function that goes from a point to a length, the function called distance, will always, if I know that I have a point, will always return a single one-dimensional distance scale. And therefore, these things fall. And I wanted to explain in that very concrete term for us literal-minded people, is that I now know as a result that A is always a point, the function called length always takes a point and gives a distance. And therefore it entails the fact that the function called length takes in a and always returns something of type distance. Sorry for being very pedantic.
Yeah, no, that part makes sense, the example. I'm still struggling with the why make it so complicated, right? Like you have turnstiles and bars, and like, obviously if you have A and apply F, you get B, right? Like, the bottom line is clear why the syntax so
Well, the
fancy.
fact that you're taking your time to go through it makes me want to be pedantic and make sure I understand it. So this is a teaching style thing.
Yeah.
So why the two different, again, back
Yeah,
to that
so
question.
that's a great question. The answer is because these derivation trees can get absolutely huge. What you really care about is the set of lines that you can use, the set of inference rules that are valid within the language. So a type theory is someone will say, here's 20 inference rules, and that's it. Those are all that you can use. And so you can use those rules to make derivation trees as big as you want. And we normally don't look at them, but they're sometimes useful, and people writing type theory papers love them. So this was supposed to be, let's teach everyone how to read them. I might have been a bit optimistic. But so
Make it sound like it's our fault.
no. It took me quite a while to learn how to read these things. So
It's not that they're unreadable, they just feel extra complicated for no reason, I guess.
I think
it's not like, it's very obvious what this is saying, I think.
Yeah.
But yeah,
That's
like
good.
why this format, I guess. But,
That's a
Yeah, I
terror
guess
on
I-
the first slide.
Like I get stuck on
okay, so-
implies versus turnstile versus
Yeah.
line. It's like, well, you're just saying if then. But
Yeah.
actually,
No, no,
there's
so-
this important distinction that kind of matters for the formal systems.
Yeah, I think that's a good point. Like, you could write, have all of this at the bottom in parentheses, and then say, all of the things on the top also in parentheses with ands between them, and then like it implies, and the line would be like the length of this wall.
Sure.
So putting it on the top and the bottom of the line is kind of just a way to show a common thing that you do, which is just conjunction implies something. It's really under the hood, just doing exactly that. Yeah.
So I'm trying to guess from like something you briefly maybe said and maybe didn't say. So you said that there's a collection of actual rules that can annotate the horizontal lines, and that is part of the definition of the type theory, like this E here.
Yep.
So the point is that we are given a collection of primitives, and then we can build our tree from these primitives. And essentially, by convention, we're only putting the primitive derivations next to the horizontal lines. And then
Yes.
the turnstile is a compressed thing where you have used a bunch of elementary moves. And you have now you have derived a more complicated thing, and then you can abbreviate it with a turnstile. Is that sort of a reasonable take? Because that's what's happening here. You kind of like, you want to start with nothing, so you have to have this like, I guess you have to also annotate the top two lines with like nothing, like, whatever. Like if you have A, you can use A. There's going to be some annotation that allows you to do that, and then on this thing. And then you have another primitive move that combines them. And now you've built this tree that starts from nothing and gives you this bottom thing.
Yes. Yeah, I think I really like what you said. The only thing that I didn't understand was that turnstile is like taking a bunch of moves and kind of combining them into one.
Well, I mean, the evidence for this bottom turnstile is the tree that we have here. So in a sense, the fact that we have the turnstile is a compression, like, of the tree that provides the verification that this turnstile implication is correct.
Yeah, I think that's a good way of looking at it. So the turnstile is like the core judgment that you get to conclude based on all the work you did.
Yeah, so like now, potentially I can forget the tree,
Mhm.
and I already have the turnstile in evidence.
Yeah.
But like, at any point that I need it, I could, in principle, kind of substitute the tree for it or something.
Yeah, exactly. And the mathematical way of viewing this is each inference rule is like an axiom,
Yeah.
and you can recombine those axioms however you want,
Okay.
as many times as you want, recursively,
Yeah.
and whatever you get at the end is the judgment.
They're derived state.
Yeah.
Yeah, I want to say one thing that I found useful when thinking about elimination rules, and I guess inference rules in general, and like let me know if this makes sense, is to think about them not as operating on like abstract like functions or types or whatever, but instead operating on like symbols on a piece of paper, right? And so when you see something on the top of the bar and something at the bottom, like it's literally saying if you have the symbols at the top written down on a piece of paper, you can erase them and replace them with the thing at the bottom.
Yeah.
Which also kind of connects, I think, more clearly to the, computational notion of like, what it means to compute using these rules, right? Is it just a process of like erasing things and replacing them, or possibly expanding something into a bigger thing? I'm not sure if that helps at all, but.
Yeah, no, that's exactly, and that's something I should have said. So these symbols are defined by the way that they're used in the set of rules that you give them. So often people will have similar looking type theories in which the symbols really mean something completely different because you can or can't do something that you could have in the other system. Thank you, I really should have said that. The other thing is that whenever you see something like A and B, these rules are always maximally universally quantified. So this means, for any A and B, you have something like this. And so the rule at the bottom is basically just function application, that you can apply functions and you get the thing that they should return. I should have explained that at the beginning, and I should have explained the symbol manipulation. I think that makes things clear. I also don't want to lose everyone. Is this good? Okay, cool. All right. Great, so this is exactly the same thing. Before you saw arrow E, this is arrow I. So this means before we were taking a function and using it. So we were eliminating the arrow. So we, took the arrow up here, used the arrow, and removed it on the right-hand side. The way that you do that is function application. Here we're introducing the arrow on the right-hand side, so that's the I, by using a lambda abstraction. So for those who are unfamiliar, which I'm thinking is not anyone, this isn't the case, lambda is basically an anonymous function. So you say, this is a thing that takes some argument, which we call A. And then this B probably has something that uses A somewhere in it. So it's the only way of defining functions within lambda calculus.
What about
Questions?
gamma and delta?
Yeah. Thank you, that's where I was going next. So gamma and delta are, this is the last tricky thing. Gamma and delta are the common names for, this is a collection of terms and their types. So, if you crack open gamma, you might see A has type A, B has type B, C has type C.
So it's an ordered list, basically, it's like before A and after A?
Yep, exactly.
So the order matters?
Yeah, why does the order matter?
Yeah, what is it?
So there are some type systems where the order matters and some
okay.
where the order doesn't. And so the ones where order doesn't matter will include an explicit rule saying, and you can change the order. So everything is by default, these symbols literally mean these symbols in this order. And if you want to say that order doesn't matter, then you include a rule saying order doesn't matter.
But then writing it in a simple prologue made it simple.
Maybe,
It feels
maybe.
very like
Well, this
moving
is
arrays
from
around.
the 30s.
Yeah.
Not for a long but yeah, so anyway, I probably would not do infinite rules if I give this talk again, when I give this talk again.
Oh,
but
well, I mean, if you read a paper in that theory, you have to
Yeah.
see this.
Yeah, that's-
There's no escaping.
that's the devil on my shoulder saying I should have done this.
I warned you.
Yeah. So the last thing I'll say is that this comma is overloaded because, I don't know, people are lazy when they're writing papers, and that really means you take gamma, you take delta, you concatenate them. Cool. Yeah.
Just to be clear, are gamma and delta here just two separate contexts because they're both in the assumptions? You can kind of concatenate them both together and get like some super, like the set union of them, I guess.
Yeah, yeah, definitely. So you can kind of pattern match on the above. So let's say we have, Z, X, Y, A, and then some other letters. Then you would pattern match and say, okay, everything before A goes into delta, goes into gamma. Everything afterward goes into delta, and then you kind of use those in the bottom. Cool. This is, I believe, the last slide with rules, with lines of any kind. Are we good? Ready to move on? Okay, nice. I'm very happy about this. Okay. So, we've talked about things that have types. We've talked about how to assign things types. We haven't talked about how these programs actually do anything. So the reason that I drag you through this hell of introduction and elimination rules is because the way that you define computation, all you have to do is define what happens when you have an elimination rule applied to an introduction rule. And so if we go back, the elimination rule is function application for arrows, and the introduction rule is lambda abstraction. So if you take something like an arrow, it's a different kind of type, for example, like a product, a sum, it will still have exactly the same form of what happens when I eliminate something that I just introduced. So this square is just, I'm saying, any kind of type former, where type former means something like an arrow. So for example, in lambda calculus, the eliminator of the arrow applied to the introduction rule of the arrow means if you take the lambda abstraction and you apply it to an argument. And so any computer scientist will say, well, of course, you take C and you plug it into A. And so that's exactly what this means. The kind of novelty here is all you have to do to define computation is say what happens for any kind of type former when you encounter exactly this pattern. The way to ensure that this doesn't go haywire is called subject reduction. And so that just means if you reduce in the way that you've defined, then the thing at the end better have the same type as the thing you started with. So for example, you shouldn't start with a function that takes some type and returns a string, and then you run it and you get an integer. So if inductively, anytime that you can run a computation, you end up with the same type you had, then in the end, when you finish, you're going to have the same type you started with. And so this is kind of the foundation of typed programming languages, especially functional programming. Cool. This is kind of a big leap. Any questions? Yeah.
No, I'm not sure I'm ready to ask a question. Especially, is it a common piece of notation to use the empty square for this, or
no?
Or is that actually a graphical typo? Like a missing emoji?
I wish it were a missing emoji. I would use like smiley face or something. No, I just use the square to mean put whatever you want within the square.
What's this?
C, I just use A, B, and C to mean anything.
But like, where does it come from on the left-hand side? Like,
Right. So the reason that this isn't trivial and that you can just kind of knock out the elimin intro is because, thank you for asking, the elimination rules and the introduction rules might have arguments. So for example, the elimination rule and introduction rule for functions are lambda abstraction and application. And to do those things, you need to provide the argument. So when you're eliminating the arrow that's in this type, you need to provide the function that you're using to do it. Sorry, the argument you're using.
Is that the same C right there? That's a lambda? Should be a small C?
Oh, sorry, this means lambda calculus.
Oh, lambda calculus.
In the specific example of lambda calculus, this
I
is
see.
the beta reduction rule.
Yep.
So the elimination carried the C.
Yes. And so the reason that you don't normally see it written as functions like this is because they're implicit arguments, and different type formers could have different numbers of arguments. And so what you need to do is you need to define beta reduction in such a way that you take all of these arguments that you need to run the introduction and elimination rules, and you come up with some way that they reduce such that subject reduction works. And this is non-trivial. Like, arguably the hardest part of defining the lambda calculus or anything like it is how do I deal with names and how do I substitute the thing into the function when I call it. So it's very non-trivial, even though it's kind of beautiful that all you need to do is just take the elimination rule and the introduction rule and cancel them out. Yeah.
Sorry, I'm now understand that I don't know what the implication arrow is. So I know I'm combining, some of the primitive rules, and then what?
Right. So
It's the formula. So it's like what I define this. Sorry.
yeah, I didn't explain that. So this just means I get to define how this thing
Combined, yeah.
evaluates to some form.
So
of
this is the definition of the beta reduction.
Yeah.
I see. Okay.
I think you suddenly went from explaining things slide by slide, step by step, to having a bunch of new terms thrown out at once. So,
Yep.
you're going to find elimination, introduction, and calculus, and all that.
Yep.
The point I'm taking out of the slide is that the dumb reader is that type former, empty square here, is being given as an example. In lambda calculus, the single arrow headed to the left is meant this, right? You're actually defining that concept.
Yeah. Thank you for slowing me down. Yeah.
the different or like a similar notion to the idea from the previous slides of like you have some statements on a page and you can erase and rewrite it to something else?
Yes.
Is it the same thing?
For the computational
Yep.
judgments, basically, right? Because you showed type judgments for the facts,
Mhm.
but they're also. Okay.
Yes. So it's a new kind of symbol manipulation that you get to define.
Yeah. Does the previous thing like subsume this?
I don't think so. It's
Like if you just use elimination rules, picking calculus,
Mhm.
and introduction elimination rules, and you just do like statement rewriting, do you get this out?
I'm not sure I completely follow.
Or does that like depend on this?
Can I have to translate your question?
Sure.
Sorry, so I'm not looking at you, saying that, if you're saying this is a lofting of the game, saying if the game was, here's a game played with straight horizontal lines and you're the prisoner in Searle's Chinese box, and all you're allowed to do is move things around and there's a horizontal line. Then the next slide is like, there's this other game you can play with this T-shaped looking thing that's on its side, entailment. And then you're saying, well, now I want to play a game with like squiggly lines. Well, then generally you're going to be introducing some terms and eliminating some terms. And in the case of lambda calculus, this is me teaching you, the idiot prisoner in the Searle's Chinese prison, this is what single arrow means in lambda calculus. So your point would be that that's what I hear when you say, your question to Will is, does this slide subsume the previous two examples, or it's kind of an abstraction above them? So first I ask you, is my question even a translation of your question? No. Are you trying to say this?
I'm not sure.
Like, does this slide build on the previous two, or is this slide an abstraction that replaces the previous two techniques?
I think the thing here is because this one's using like the notation of function application, whereas the previous slide had like lines to do the deductions. The deductions seem to be operating by functions here.
Yeah, I think a larger point from this is that notations collide a lot, and I should have done a better job of pointing out when things mean different things. But this is extremely common in type theory papers, and it's not always clear what things mean. But I think to answer your question, so elimination on the type level doesn't mean the same thing as like eliminating a function by applying it to an argument.
I think the root of my conclusion is like the ontology context thing of like, here you're trying to derive true statements using some introduction rules and like you care about the truthiness of the statements. And then the lambda calculus, it's purely just rewriting. There's no notion of truth.
You postulate that your basic rewrite rules preserve truthiness?
So that's why I'm imagining thinking about SQL calculus. I'm like, oh, it's a system for deriving new true statements. Where lambda calculus seems like more like a component of that.
I think you're getting to something that I was hoping we would not get to yet. But okay, so I think I'm going to basically say that we've covered this enough. I haven't done a good enough job explaining it, but I don't think this is essential for getting through the rest of the presentation. So I want to go through something more concrete so that I don't lose everyone. Okay, cool. All right. This will be difficult, so I'm going to skip it. Cool.
You spent this whole thing arguing that the letter O and the letter R, that I think of as or, you're explaining that? That's all we skipped?
It's a really cool thing about why computation matters for proofs, but I hope that we can get to it later. And I'm going to go through something more concrete so that we can kind of bring everything back to earth. Okay, cool. I'm realizing that I'm no longer on my own computer.
Do you want like
the terminal?
yeah let me give me 1 second.
Okay. And do you have Lean installed?
Yeah.
Or VS Code, or whatever you want. Yeah.
Actually, I was just doing.
Coffee break.
If there is a break, can I ask a question?
Yeah. Please.
So-
This is difficult, and I haven't done a great job.
So the
explaining it.
kind of like the lambda calculus based type theory, it seems like, I don't know, not intuitive, but like, how to say, I sort of have an idea what it's supposed to be talking about.
Mhm.
But you mentioned that there might be type theories where like the arrow is not an arrow but like a product or something, right? So is there like a simple enough version somewhere? Maybe like I can ask you later for like, because I think it would be illuminating to distinguish between like interpretation and formalism. If you have more than one example, especially one where they sort of diverge a little. So like if I had something where this box was not an arrow but like a product, then I could see how the elimination and introduction work in that context, and how their composition would correspond to some beta reduction rule, which is not just, you know, application to a particular value, right?
Yeah. So
Are
I
there
can,
such toy examples that one could look at?
yeah, I can easily provide just verbally one example, which is if you look at you know, like a pair. So you would take a type A and B and produce, you know, a tuple of A comma B. The introduction rule would be applying the tuple to A and B, and the elimination rule would be taking the first element or taking the separate element. So there are two different elimination rules.
I see. Okay.
And
there
so
are two different beta reductions?
yeah. So you would say, you know, if you have the pair A comma B, and you take the first element, then that is better reduced to A.
Yeah.
And if you have the pair A comma B and you take the second element, then better reduced to B.
Okay.
And so that's exactly the same kind of formalism as function application.
Sure.
It's just that function application is a hell of a lot more complex, and that's where a lot of the interesting computation is.
In fact, you can build it out of functional application, but you can also take it as a primitive in the field.
Yeah, yeah, and
you can build pairs with lambda calculus, but also you can say they're primitive to the theory.
Yeah, but I think that's more interesting from a point of view of like eliminating the whole formalism tree.
yeah. And maybe I shouldn't have chosen the lambda calculus, because the thing about the lambda calculus is, as you said, you can build everything out of just function application.
Well, I mean that's the core example, but like I think like having core example and the toy example together or like whatever.
Yeah.
Anyway, thank you.
You're absolutely right. Yeah, I had an interview this morning and made these slides.
Okay. You're set.
Okay, I'm glad that everyone is still here and that
Your
no one's
setup is
left.
ready.
Okay. Cool.
Let me know if it works.
Yeah, that's great. Thanks. Great. So I was going to do this in Rust because it's not a theorem proving language, but Lean's going to work. Oh, do you have the mode?
Yeah.
Nice. Okay. Cool. So who here is familiar with algebraic data types?
You're on my shirt today.
Nice. Okay. So for everyone who isn't, it's something that you've surely seen already, and that is going to be immediately obvious, but it has a very mathematical name, and it has a name for a reason. So the thing you can do is to find something like, so let's say, this is already a type in Lean. Let's pretend it's not a type in Lean. So we can say, for example, if you have an option of some type T, then it can be either none or some constructor applied to some argument. It's yelling at me that it's already been declared. So let's say optional.
Maybe.
Great. Oh boy. Computers are always trying to be helpful, aren't they? Okay. Cool. So
Do you want option?
let's ignore the red square.
Oh.
So
Not
yeah, this is a very simple example of an algebraic data type. So all that long name means is that you have potentially multiple ways to make a thing, and all of those individual constructors might take arguments, and they might take different numbers of arguments of different types. So, for example, as an option, you can have, let's say, oh boy, list of some T, where you have, you know, the empty list, or let's say, append some T of some type T to another list of type list T. So it's the same kind of thing.
Lean for T?
Yeah, sure.
Put it that way. Oh, you have to get rid of the error first.
Yeah.
Let's rename it to list one. It's plus.
But then list one is
List
list one.
T
Right?
now. Okay,
Type U1. Yeah, so we'll get to the
Universe
U1
world.
if we have time.
Do you want the other one to be list one as well?
Option. Oh,
Yeah.
the other one.
Good point. Great. So, in short, this is all that an algebraic data type is. It is the single biggest thing that I miss in languages that don't have it. It's extremely, extremely simple, and the nice thing about this is, for example, if you're writing a function that takes a list, then all you have to do is match on the list, and it can be one of exactly two things. You just have to kind of, if it's empty, then I do thing 1. If it's append, then I do thing 2, and usually a recurse. So the power of this kind of construction is that you can build practically everything that is interesting out of algebraic data types. So for example, you could, normally have structures or records, which is just, you have a bunch of fields, and they're all the same number of fields. And so that's just a singleton, where the only constructor has type, these things.
Is there an easy example of non-algebraic data type?
Yeah, you could say like a not only, but
Yeah.
you could say, for example, a structure with some arguments. So the reason that this is not algebraic, even though under the hood it is, but syntactically, it's because you're not enumerating all the ways that you can make the shot. You're just saying implicitly there is exactly one way that I can make it. And what I'm saying is that's exactly the same as saying an algebraic data type with exactly one argument. Exactly one constructor. Is this making sense to everyone? It should be extremely simple. Cool.
I think the interesting part in Lean is not only all computation can be done with algebraic, that is all logic that we do in Lean also is done through algebraic.
Yeah, exactly.
So theorem proving is also done with the
Mhm.
same kind of methods.
Yeah, that is absolutely amazing. And to kind of
Sorry if I saw you.
no, you're good, you're good. So there's a deep reason why it's called an algebraic data type. It has to do with category theory, but we don't have to go there. The interesting thing that you can do is you can write something like option t as an expression involving addition and multiplication. So you could say, for example, there is exactly one way that I can make none. So I would take 1, and then plus, there's a different way that I can make this thing. So plus the cardinality of t. So option t is in some sense equivalent to 1 plus t, in the same way that a power set is 2 to the whatever, because the cardinality of the power set is 2 to the cardinality of the thing. So there's this notation where option t is equivalent to 1 plus t. List 1 is, you have empty, there's exactly one way to make empty, plus all of the ways that you can make append. That's plus t times list 1 of t. So this is kind of a recurrence relation where you're saying, this expression tells me exactly how many ways I can make something of this type. It's very, very deep. Briefly, I'll just say that if you take a partial derivative of this expression, you get a really, really interesting data type called zipper, which is the same thing but with one hull removed. It's not just like a cute, notation. There's a very deep correspondence here. And so, if you remember back to a few slides ago, where we had true and false represented as 0 and 1. So, for example, true and true is 1 and 1. That's very common in logic, and the reason that that's very common is, 1, because that's how bits are made, but 2, if we think of 0 and 1 as algebraic data types, we can think of, okay, how can I write down 1? So you could say, I know that kind of the algorithm to take this notation and turn it into an inductive data type is you take all the pluses, all of those items become constructors, and all of the times become fields. So you could say, 1. So we know that 1 has to have exactly one constructor, and that one constructor shouldn't take any arguments since there's no multiplication. Cool. Now if you think about 0, we know that 0 is the thing that you can add to anything and not change. So the way that you write 0 is you have no constructors whatsoever. And so the point I'm going to make is that there's a very, very deep connection between these two very simple algebraic data types, and I'm going to move them up so that everyone at the bottom can see. There's a very, very deep connection between these two data types and the logical 1 and 0. How is that? Well, this is the part that I didn't cover when I skipped a bunch of slides. But the benefit that you get from encoding computation in your type theory or logic is that you get to say, if I have something of this type, like if I have something of type 1, then when I run the thing, when I evaluate the final value, it's going to have to form one of these constructors. That's the kind of soundness of the type system. So 1 represents a trivially true statement, 0 represents a trivially false statement. So 1 is trivially true because you can just construct it, and 0 is trivially false because there is no way to construct it. And so the way that you would say, is this a good type theory, is this a bad type theory, is can you make a term of type false? Which means can you construct, can you trick the type system into thinking that there's some value that I can't really create? So that ties back into subject reduction, and if I run the thing, no matter how long I run the thing, it better have the same type at the end as in the beginning. Cool. Is this making sense? Nice. Yeah.
Do you want to do a quick test? Write false and command click on it. We can see
Yeah, nice.
where we end up. Def.
It's a crop.
Yeah, yeah, exactly. So now we're gonna see inductive where empty.
Yep. So that is
There it is.
exactly how false
Yep.
is defined. So the reason that I'm doing all of this, and the reason that I went down this rabbit hole of inference rules and all that good stuff, is going to show you what's going on under the hood in Lean. The reason that I think this is valuable, even though I think at some points I've lost a bunch of people who have done a great job explaining, is because I kind of think you don't really own a car until if it breaks down you can open it up and fix it. And so you should really know, like, this is how false is defined. You should know how exists is defined.
You didn't promise self-driving cars that never break down. Why do I need to read the prelude?
Well, I mean, Lean also promises you that the kernel is sound, but you better go out and make sure. Cool. So I guess at this point, we're almost at an hour. Does everyone want to continue, take a break, go down some other path? Okay, I have more slides.
Is it a promise or a threat?
That's up to you. Yeah,
I like all of them.
Also, yeah.
They are,
What are the slides?
there's a lot more
What's on the main
inference rules.
There you go.
Cool. So there are more slides that are more applied and fewer inference rules and forms. Here are the slides that I skipped over for you. Do you want me to go through them? I don't think this is going to go well.
Give it a shot.
Okay, all right, very briefly. I'm not taking any questions. If you get it, you get it. All right. So, for example, let's say we have, someone says, I have this great type theorem, I have this great type theory, and within this type theory, I have a proof that A or B is true, where, pick your favorite A or B, instantiate it with, Goldbox conjecture, or, whatever the hell you want.
Remember the natural numbers even or odd?
Yeah, sure.
Okay.
Every natural number is even or odd, or the Riemann hypothesis is false, right? And they say, I have this great type theory where either this thing or this thing. What we want to do is we want to make sure that that or within the theory really means or in plain English outside the theory. So you shouldn't be able to prove that A or B without showing me a proof of A or showing me a proof of B. And so the idea is you should be able to take the entire derivation tree of A or B and look above, and somewhere in that derivation tree, you'd better be able to find either a proof of A or a proof of B with no preconditions. That kind of make sense? Okay, cool. And I'm not in presentation mode. Cool. So that's exactly what I said, where you take, this is the final line. Below this you have A and B. You have no context, so given nothing, I can show you that A and B is true. And these dots mean there's some derivation tree. We have to figure out what's in it, but whatever is in it, it had better have a proof of A or a proof of B. And so what we can do is, because we have a finite set of rules, we can look at, all right, how could this have been created? So we can kind of iterate over all the possible rules that could have had this at the bottom and induct on that. That's the basic proof technique that we're going to follow. So the, the emoji is not rendering, but this should be a green check mark. So this means if we take the OR rule, where you take whatever's on the top and you throw it on the left, and you get to put whatever you want on the right. So that's OR left.
Yeah.
That checks because we have this on the bottom. If we apply OR left, then we know that that has to be on the top. That's proof of A, so we're good. Similarly, we can do the same thing on the right. And the thing to notice here is that, for example, you can't have an AND rule because the ANDs couldn't have an OR at the bottom. It just wouldn't work. So you have to kind of pattern match and say, what inference rule could I have used to get the thing at the bottom? And there's only one such more inference rule. This is the problematic one. What if I had some hypothesis? Again, sorry about the typographic issues. What if I had some hypothesis called C? We don't know anything about C. But I used C to prove that A and B. And then over here, I proved C. So the problem here is we're inducting on things that have OR on the bottom. We don't know anything about C, so C might be a proof of agreement hypothesis. That doesn't have the shape OR, so we can't use our inductive hypothesis. So we're kind of stuck where we have this hypothesis that we don't know anything about, and it's killing our inductive procedure. But the thing to note here is that all of the other applicable rules work. So what can we do to get rid of this C? So the idea is we should be able to take the derivation tree that uses C and come up with some equivalent derivation tree that doesn't use C, so that we can show that within that one there's a proof of A or B. So how do we do that? Well, if you look at these issues. So if you look at, for example, here we have C implies A or B, which is the only way that you can get something like C on the left implies A or B on the right. Then we're good.
So is the problem with 3 on the left or on the right?
The typographic issue is on the left.
No, not that problem. The
Oh,
problem
sorry.
we're trying to solve, we're trying to find, do we go left or right?
Yep.
It's all on the left, right?
Yeah, you're
So
not gonna.
I'm taking this
Yeah.
and I'm blowing it up to full
Yeah,
size.
I get that part. Yeah.
And then the problem is kind of the whole thing at once.
Oh, I see.
So we have
The right side's also?
Well, we're not gonna find a proof of A or a proof of
Right.
A on the right. We're
So
only
we
gonna
have to
find
go
it on the
left.
left. So we have to argue that we'll find it on the left.
But even if you find it on the left, it still probably has a C in it.
Yes, sure.
And so you can't show that.
Yeah, but then we need to eliminate. You need to like maybe take the one on the C and like use it to eliminate the C on. Is that the idea?
I think you're going where I'm going,
Okay.
which is, so we have, we introduced some hypothesis C, we proved it over here, and then over here we used the proof that we came up with over here to prove A or B. So what we should be able to do is realize that we just eliminated something that we just introduced, and take the C over here, the proof of C, and kind of inline it on the left.
Yeah.
So we can take the full proof of C
Yeah.
and inline it and remove C from the bottom.
Yeah.
So the way you do that is with something like this, and you should be able to cross out everything that's in red. And then if you look at what we just did, that's exactly beta reduction and subject reduction for proofs. And so if that makes sense to everyone, I kind of pulled the wool over your eyes and said, we have this thing we want to show, which is that these axioms mean what they mean in natural language. And the way that you prove that is by introducing computation on proofs. And that's kind of, it's a very deep thing that I'm trying my best to explain, but the typography is making it difficult. So this is kind of an informal argument for why we should care about computation. It's not necessarily the case that computer scientists just wrote these proof assistants and included computation because they could. It really, really helps with, even if you aren't running programs, you can show that nice properties about your system. Okay. I said I wouldn't take questions, but I think that went better than I thought. So, yeah.
Quick question. If you have the function C to A or B, why don't you instantiate that as a thing we don't and look inside it? Is that are you not able to do that, or sure you would just look inside the procedure that takes you from C to A or B?
Two things. First, I should have noted that this is just logical implication.
Yeah.
And then second, if you want to look inside C, then what you're doing in the middle of the proof is kind of, this is an induction. And if you were to look inside C, you would be running another induction within that
But you
step.
can't look inside the implication? Generally, no?
You can, let me go back and do this in slight bit more detail. If you look at all of the ways that you could have come up with C implies A or B, there are exactly two ways. So the first way is you have C on the left side of the turnstile,
Yeah.
and you just do the syntactic rewrite, which just arrow means the same thing.
Okay.
You can say C equals A or B. Or, this is the problem, you could have another hypothesis D that tells you that C implies A or B. And so the problem just keeps getting worse.
Ah.
And so the only way to resolve that is to say that for any proof, I can run it by substituting in proofs of things that I already know exactly where the hypothesis is.
Okay.
Yeah.
It's kind of getting back to the thing before where it's like m-progress is embedded in here, kind of.
The rules are very similar, yes. And there's a deep reason
Are they not
there.
the same?
They are exactly the same, yeah.
So it is embedded in like you're redefining the rules of m-calculus, using the rules of ZK calculus.
The thing I wasn't going to tell you is that the rules happen to be exactly the same, but nobody wrote them that way. The rules for simple logical implication and for lambda calculus are exactly the same.
Like Howard correspondence.
Yeah, exactly. It's a Curry-Howard correspondence. Yeah.
What are you assuming about the context in this argument? Like, if A or B was literally in the context, then A or B gives you A or B would not allow you to pull out A or pull out B. So, what does the beginning look like here to know for sure that the A or B just wasn't already there?
Yeah, so that's, okay, thank you for asking that. So that's, if there's nothing to the left of the turnstile, that means that there was absolutely nothing over here. And so the idea is to kind of prevent what you're saying by saying, the rules that you give me for your type system, for your set of implication rules, can't introduce something like that because it would be unsound because they would just do simple things you said. So the idea is you start with a proof that nothing implies A or B, meaning that A or B always wins. And you have to verify that you really proved either A or B. So is that kind of getting what you're saying? Like you shouldn't be able to just introduce the same thing on the left-hand side.
Okay, so the claim is that, so we're looking at tautologies then. If A or B is, it's only possible for A or B to be a tautology if at least one of A or B is a tautology.
I think, but you get to define what the symbols mean. So it's kind of, the game is saying that these symbols mean what you want them to.
What's something you can derive? What is a derivation that can be done from absolutely nothing here? Like, what is a situation in which we have blank turnstile egg?
It depends on the rules that you're given. So you could say, for example, like if we're working in, intuitionistic propositional logic, then you would have a different set of axioms that you use. And if we're working in classical logic, you have a different set of axioms. And so the idea here is like, you're given some derivation tree, and you don't know what the axioms are, but you can run induction. And so the idea is like, it should mean what you think its ontology should be. Yeah.
And the whole premise was like, we really wanted to know, did it come from the left or the right?
Yeah.
So doing classical mathematics, you have